So before we get started with the actual material, I also wanted to give you an overview of your Univariate Statistical Toolbox that we will develop in this class. So these are the specific methods that we cover in rr480, 580, organized by objectives and data type. And that may be a useful video to occasionally come back to, just for you to put what you learned into a bit of a broader perspective so that you know where you are and why we're doing particular things. So let's take a look, and I like to organize this into objectives, so what you actually want to do or can do, and into data types. So we have the normally distributed data, non-parametric data that does not follow normal distributions. And we also have binomial data, so that's binary data, yes or no, dead or alive, healthy or infected, and so on. So these are all common data types that you have to deal with, and different methods are required to analyze those properly. So one thing you might want to do is just describe your data, either through summary statistics or through graphical summaries. So there are different statistics that you can use if you have normally distributed data. Means, standard deviations, variances are fine. If they are not normally distributed, you usually use the median, quartiles, or quantiles. And for binomial data, you have to report proportions. So there's like 50%, 20%, and so on. And you can also display those things graphically. So we have scatter plots, line plots, bar charts, and dot plots with standard deviations, standard errors, and confidence intervals here. This only works for normally distributed data. We have another set of graphical tools for non-parametric data, box plots, histograms, or if we can transform the scale, then you can also use the parametric graphics. And for the binomial data, you can actually also use most of the parametric, except that your standard errors and confidence intervals, they will not be symmetric. And it's quite easy to imagine if you have, for example, a value of 0.9, your confidence interval is not going to be symmetric because they bump against the 1, so they can't get larger than 1 at one end, and they can't get smaller than 0 at the other. So they're bounded by those limits for proportions. So those are the first units on numerical and graphical summaries of data, and then we'll move on to inferential statistics. So those are the ones where you run tests and get p-values. And we'll spend quite a bit of time developing the first one. It's the very first inferential test that was invented by William Gossett in the early 1900s. So William Gossett was the head brewer at Guinness, and the Guinness brewery actually did not allow him to publish this or to even tell anybody else. They considered this a trade secret and competitive advantage they had over other companies. So just to give you an example how you can use a one-sample t-test is, for example, in quality control, you can make a statement, I guarantee with 95% certainty that this batch of light bulbs will last at least 10,000 hours. So statements like this you can make based on a one-sample t-test. And this invention was really a big conceptual advance. So Ronald Fisher, who is really considered the father of statistics by many, he always acknowledged, and I quote, Gossett was the one who effected a logical revolution with this train of thought. And so we'll spend some time putting ourselves into Gossett's shoes and follow his thought process. So once you understand this test, you understand the fundamental principles of everything else in this whole toolbox. So the next test here expands this to 2 samples. So you want to compare 2 things, which could be 2 light bulbs or maybe 2 fertilizer treatments. So you're wondering, is one treatment better than the other? And usually you don't just want to know whether they're different from each other, but by how much. So you can make statements such as fertilizer A is more effective than fertilizer B, increasing the yield by at least 20% with 95% probability, something like that. So for those types of statements, we will use effect size statistics and confidence intervals. And you can also add a decision analysis to this. So that's an important component because perhaps the fertilizer A is actually twice as expensive as the fertilizer B. So even though it is better, it may actually not be a good choice to use it because a 20% increase in yield just does not justify the cost. So these are all important questions. So most of the time, you don't just want to know, is it different? No. You want to know by how much and what treatment actually makes sense to use. So this makes this course a little bit different. So we'll spend quite a bit of time to actually solve applied questions and provide actual decision support. There's also a version of the t-test that works with paired data, so there are not two independent samples A and B, but they could be the same samples before and after some sort of treatment. So it could, for example, be a survey of knowledge before you take a course and after you take a course. And so those are actually paired observations. So that paired t-test is better in detecting differences than if you were to apply a two-sample t-test. Now, if you have more than two groups, so A, B, and C, for example, then you're in the analysis of variance territory. And again, we'll do the effect size statistics and general linear hypothesis testing. So this part is actually not all that easy, but super useful again. So if you don't do this, you're leaving money on the table. And ANOVA will give you very little information. If you get a p-value, it usually does not mean a lot. It doesn't tell you what to do. So you do have to follow that up with specific contrasts that help you make decisions. So next we'll have multi-factor ANOVA. That's the extension of a single-factor ANOVA. For example, if you have different levels of fertilizer and different levels of irrigation, you can look for something that's called interactions. So what can happen is that if you have high levels of irrigation, then your fertilizer treatment works really well. But if you don't irrigate, then fertilizers are actually having a negative effect. So finding interactions among different types of factors, that's an important part of science actually. So this one here is also an important tool. And then the last two objectives here, they apply if your predictor variable is not a class variable that you control, but they are continuous. So for example, instead of irrigation levels, you might have just rainfall observed in a sampling design. If you're looking for how one variable affects another variable, or if you want to predict one variable from another, then we have a correlation or a regression problem, and we cover those as well. Now, everything we've discussed in this column, you can also do for data that's not normally distributed or for data that is binomial. And we cover a number of easy to implement modern techniques. Those are generative models. So that includes, for example, bootstrapping, permutational tests, Monte Carlo simulations. So these tests can do everything that we can do with parametric statistics, as good or better, but they can require some considerable computer horsepower, and they're also sometimes not very easy to set up. So we only cover the easy ones here. So the more difficult ones that are the foundation of Bayesian statistics, we'll skip them in this class because we just can't do everything. And you will see that we actually can get things done very well by ignoring some of the assumptions. So if your permutational test gives you the same answer as the parametric test, then you can often just ignore those assumptions for things that would be difficult to set up here and use parametric statistics. And the reason that you can do that is that the assumption of parametric statistics is actually not that the data is normally distributed. It's that the statistics, like the mean, that they are normally distributed if I were to repeat my experiment over and over again. And that assumption is usually actually fulfilled. So in many cases we can get our answers without running these computationally intensive tests. And secondly, we also have a suite of classic non-parametric tests. So these are rank sum based. So instead of analyzing a value, those values get converted to ranks. So you just order your observations from the biggest to smallest, and then you can do statistics like the Wilcox test, the Mann-Whitney-U test, Kruskal-Wallis, Friedman, Spearman. So these are all rank-based tests. They're old-fashioned, but they also have an important role, and I briefly want to explain why. So if you work with ranks and not values, your tests are actually comparing medians and not means, and that can be important. So let's say you're a political analyst and you want to evaluate policy prescriptions that raise the income of Canadians. Now, one thing you could do is you could make policies that make billionaires out of all the millionaires, and that would certainly raise the mean income by a large amount. And if you wanted to test whether those work, then the correct test would be those modern generative models because they work with the values. However, If you're a policy analyst for the NDP, you may be more interested in your typical Canadian, and in that case you are interested in the median income. So you want to raise the median. So if you're testing effectiveness of policies on changes in median income, you need those rank-based methods. So in highly skewed distributions, the median may be the more important factor that you care about. Sometimes you actually do not care about the median. You do want to test differences in the mean. So in medicine, for example, you may have a disease severity score and you want to see if a set of medications makes a difference. And in that case, you actually care about that long tail. If you can rein in the severest manifestations of the disease, so the long tails or the billionaires and millionaires, that's actually your focus, right? So you want to be sure that your medication has an effect on those. So both of those types of tests are necessary, and we will cover a full suite to cover all these objectives. And last but not least, we have the tests for proportion. So these are also interesting. There are also different types. You can actually calculate variances for binomial data. So almost everything that you can do for parametric data, you can do for binomial data. And there's a couple of other tests that we will cover that have their niche. The chi-square test, for example, is in a class of its own. That's a close equivalent to analysis of variance to compare two groups or more. And there's actually two versions of this. So one is a chi-square test of independence, which works with classical binomial data. But there are also instances where you actually only have half of your binomial data. So if you have just presence data from birds that you heard in a forest or some sort of catch per unit effort in a river, you don't truly know what's absent. But you can still do statistics with this in a modified version of the chi-square test, which just works with half of the data. So half of your contingency table can be good enough. You don't have quite the same statistical power, but it's good to know that you have this option for this type of data as well. But I think that does it for now. So everything that's in black here is core curriculum. Everything that's gray or in parentheses, we don't usually cover. There are some optional labs that cover these things if you need it in your projects. So we have an almost completely filled out matrix if you need it. We will cover mixed models in some depth, but in an optional lab. So I don't want to overload you. This is already a fairly ambitious agenda for an intermediate stats class, but you get a full toolbox that allows you to do almost everything in univariate statistics.